Thanks for coming. So today we have the Denis Bulavka. Yeah. Did I pronounce it correctly? From Israel. You will talk about Erdős-Ko-Rado.
Thank you. Thank you very much for having me. Today I'll talk about some pairwise-intersecting family theorems for simplicial complexes, and all what I will say today is based on joint work with Ras from University of Primorska. So let's start from the original setting. So this is about pairwise-intersecting families. So we will need a family of case sets where we'll have some ground set with n elements, and we just take a family of case sets, and we'll say that it is pairwise intersecting whenever we take two elements in this family, these two elements have an intersection. And there was a question in the 60s, how large can this be, right? Well, you need to choose a certain range for the parameters. So if k is larger than n half, then you can take just all the family. But if k is at most n/2, then this was not a non-trivial question, but it was answered by Erdős-Ko-Rado in 61, and they provided the best upper bound, which is, one might think, like if you try to build a large family for this problem, you might think of fixing one element and consider all the case sets that contain this element, right? So, right, this is clearly pairwise intersecting, and its size is n-1, choose k-1, and they show that this is in fact an upper bound for any pairwise intersecting family. So pairwise intersecting, and the size is at most n-1, choose k-1. And moreover, if we have a slightly stronger hypothesis, concretely if k is strictly less than n/2, and f has size n-1, choose k-1, then it must be of this shape. Okay. So then there exists x such that f. Okay, so we have a characterization of maximal families and upper bound, and the natural next question is, if my family is not in this regime, if my family is not the extremal family, what is the next best upper bound? Right? So if you are not of this of shape, like this star shape, then this inequality is strict, but what is the next best upper bound? And for this, Hilton, Milner, 67 answered this question. For it, they build the next family. So if not everything has this fixed element x, well, there is some other family which is disjoint from x. So now you have to fix some element x and some k set such that x is not there, and you can define the Hilton-Milner family, which is all the k sets that contain this x are intersect B, and you just add B. Okay. So this is again pairwise intersecting by construction, and the size of the Hilton-Milner family is exactly n minus 1. So you have everything that contains 1 minus those things that contain 1 but are disjoint from B plus B. Yeah, all of them have the same size. And so Hilton and Milner show that if you are pairwise intersecting and the intersection of all the elements is empty in the family, then the size is at most that of the Hilton-Milner. Okay. And this type of theorems, these pairwise intersecting type of theorems, they can be stated in a lot of settings, like permutations. There's a notion for permutations to be intersecting, and there's a characterization for largest families of permutations that are intersecting. For collection of subspaces over finite fields, one can develop the same theory, and for subspaces of subspaces where there is some notion of intersection. But we will stay with sets, but I want to say a different phrasing of the Erdős-Ko-Rado theorem, which is using the Kneser graph. So one can also interpret it in the following way. So the Kneser graph K and K. So the vertices are K sets, and two vertices form an edge if they are disjoint, right? So if we are looking for an independent set in the Kneser graph, this is a pairwise intersecting family. And so what Erdős-Ko-Rado says is that the independence number of the Kneser graph is n minus 1, k minus 1. Okay. So, and okay, just for complexity, we know that the chromatic number of the Kneser graph there is something called the vertex criticals subgraph, meaning that is the minimal minimal subgraph that has the same chromatic number of the Kneser graph, and one such subgraph was found by I'm pronouncing this wrong, but so I will write it. Schreiber. Maybe some German speaker. So it found vertex critical subgraph of K and K, and this vertex critical subgraph is induced by looking at separated sets. So what are separated sets? Basically, you put your vertices in a circle, and you look at K sets that do not have adjacent vertices in it. So, if, for example, this would be a separated set of size 3. Okay. Yeah. So the chromatic number is the same by definition, but so what is the independence number? We have this. If we have these K sets, we look at the induced subgraph of the Kneser graph, and we ask what are the independent sets. And another way of saying the same is we are looking at the independence complex of the cycle, and we are looking at a k-sets of the independence complex of the cycle, and what is the largest pairwise intersecting family of independent sets of size k. And this was conjectured by Holroyd and Johnson that the same situation as in the Erdős-Ko-Rado theorem holds in this setting, that is the largest pairwise intersecting family of this type of k-sets will be the one containing some element, and this was indeed proved by Talbot in 2002. So what we are looking at is one way of generalizing now the Erdős-Ko-Rado theorem is changing the graph here. Instead of Cn, we can consider maybe a bipartite graph or more general chordal graphs.
What was the this independence complex?
Yeah. So
I think I know what it is, but
Yeah.
how does it relate? You're looking at the K skeleton,
yes.
Uh-huh.
So
or the K minus one skeleton. Because there you're considering K tuples, right?
yes, the faces of size k.
Uh-huh.
So what is Cn again? It's an n cycle.
Yes.
And you look at the clique, simplicial independent
Independence
of n cycle.
of
You
n
look
cycle.
at the case level.
Yes.
And suppose these, you take a
What is the
subset
largest
of this
intersecting cell?
pairwise intersecting, how large it is.
Yeah. Yeah, I will state it like concretely in a second, but yeah. So this at least as far as I know was the motivation first step for looking at the Erdős-Ko-Rado theorem in simplicial complexes. Yeah. So concretely the conjecture. To state the conjecture, maybe let me remind that a family of sets is a simplicial complex if whenever we have K included in B, which is an element in K, then A is also in K. Simplicial complex. So for example, the independent sets of a graph G is a simplicial complex. Whenever you have an independent set, any subset of it will be also an independent set. Yeah? Holroyd, Talbot in 2005, and later Borg 2009, they conjecture the following, which is a generalization of what I said before in a way. So if you have K, simplicial complex, and now the question is what will play the role of n in this setting? Like number of vertices will not work, and so what the quantity that plays the role of n here is with the minimal facet size. So what do I mean by minimal facet size? The element of a simplicial complex are usually referred to as faces. Facets are maximal faces with respect to inclusions. You might have facets with different cardinalities. Look at the minimal cardinality. that's D. So K goes D over 2. F pairwise intersecting family of faces size K. And so then the size of F is at most max over the vertices, all the elements in K containing some vertex. And in the Erdős-Ko-Rado we have two parts, and the second part is if the inequality is strict and F is equal to the max. This max. Then there exists a vertex such that is equal to this family. Yeah. Usually when a simplicial complex satisfies the first part for some k, we say that it has the k EKR property, and if it satisfies the second part, we say that it has the strict EKR property. Yeah. So, for example, what Talbot showed is that this complex has the k EKR property for k, in this case, at most n over 2. So this, like maybe this conjecture is not so known, but there's another conjecture that's probably more famous. Like Plato. Which says that if you have a pairwise-intersecting family in a simplicial complex, then the size of this family is bounded by the size of the largest star. Oh yeah, I forgot here to write that these F's have size. Okay, sorry. So this is a uniform version, and this is a non-uniform version.
Here,
Yeah.
those are Collie Fs, and in the definition they are plain F, right?
Yeah. This is. Sorry.
Plain F and Collie F.
Yeah.
Looking
I tried to. Yeah. Sorry. Sometimes it's convenient, sometimes it's not. Okay, so another example is if K is the simplex, then this is the Erdős-Ko-Rado theorem. So why the minimal facet cardinality? Why are we changing the parameter? So I find the following example. Somehow this is what one would conjecture intuitively, and so, but this parameter might look a little bit strange. So there is an easy example to see why the minimal facet cardinality could be the right thing to look at, and it's given by it was given by Holroyd and Talbot 2005, where if you consider G disjoint union of two bipartite graphs, and you look at the independence complex of this graph. So the minimal facet cardinality is 6. Yeah? Is 6. And I claim that it is not 4 EKR. So that means that there exists a family, pairwise intersecting family, which is larger than the star of one vertex. Yeah? So we have our 6 set of vertices. So what is the size of a star? Doesn't matter which vertex you pick. So you can pick this vertex, and so the 4 sets such that everything intersects this vertex. Well, you have these 4 sets, 2 plus, then you have 2 here, 6 here, 6, and the same.
So what is K here?
Yeah, so K in this case is the independence complex of G. G is the disjoint union of
So you are looking for 4 sets.
4 sets.
Don't you need K? Oh, so you are
Yeah, so
saying
I'm
K is above D over 2.
Yeah,
Is not sure.
yeah.
Okay.
Something wrong.
yeah, in order to motivate the D over 2. And similarly, if we consider these 2 sets over here, we have the same options on the right hand side. And alright. And the last one is, if you consider these 3 guys, plus 6 again. Yeah? But what you could do instead of this is consider exactly the same family, but you remove the only thing you can remove, which is taking 1 here and 3 and 3. Instead of taking that, what you do is you take these 2 guys and then this. So this adds 6 and the rest is the same. And this family is larger than the other family. And one can play the same game to show that it is not strict 3 EKR. So what does it mean to be not strict 3 EKR is that there exists family of 3 sets, which is different from the cone, that attains the same bound. Yeah, and again, one just takes these 2 sets and 1s, these 2 sets all 1s, these 2 sets and all 1s, and then these 3. That's not a cone, and it attains the same bound. So, and Holroyd and Talbot, they show that indeed when you take the disjoint union of 2 complete bipartite graphs, they satisfy the conjecture for the right frame parameters. So what else is known? Well, there are a couple of a sequence of articles by Holroyd, Talbot, Hilton, and Spencer, where they show that certain disjoint union of certain graphs satisfy the conjecture. For some of them, it's only known the first part. For some of them, both parts is known. but usually in these results, one adds an isolated vertex. So you have a disjoint union of graphs where one of these disjoint union is one vertex only. Then there was a big result by Borg in 2009 that he showed that the conjecture is true if k is shifted, which I will say in a second, or if d is large enough. Like if d is at least cubic, the size of the faces you're looking at. And in similar, and this conjecture true, I mean, he proved both parts, the strict and the EKR and the strict EKR, and Kupowski in 2023 showed that the EKR property holds if D is at least CK log K, so it's a recent improvement. And in the direction of, for specific graphs, Robert and Kamat show that it's true for chordal graphs with an isolated vertex. And when I say for graphs, I mean the independence complex of the graph.
Well, which results are for general complex?
Yes,
and which
thank you. Yeah. So this one is only the EKR part. This one is the EKR, and this one is both. Yeah.
Oh, but this K shifted, that's any simplicial complex, or I
Yeah.
mean, not every simplicial complex is an independence complex.
Yeah, for any simplicial complex. Yeah.
Okay.
What is T complex?
Yeah, thank you. Just so there is an operation called combinatorial shifting, which basically you order your vertices. I mean, you can just order, and and you want to translate the elements of your family from higher vertices to lower vertices. And so what you do is, for every element in your family, you shift W to V as follows. You will replace the higher vertex with the lower vertex V if you can, meaning that the higher vertex is in your family, the lower vertex is not, and if you do that, you don't get somebody that is in the family. Otherwise, you say the same, and the operation. This is to one member of the family, but if you apply it to the whole family, it means that you apply it to every member. And family is shifted if it is invariant under this operation, or in other words, family is shifted if whenever you have F there and you replace any vertex by a lower one, you already have that element in the family. So if you take A less than J, and F is shifted, then for every F in the family, F minus J union I is already in the family. Okay. 1, 2, 3, 1, 2, 4, 1, 2, 5 is a family of three sets that is shifted, because 5, I could replace 5 by 4 or by 3, but they are already there. And just wanted to mention one more result. Woodruff showed in 2010 that the EKR holds for slightly more general than just chordal graphs, but the notion that generalizes chordal graphs in a sense, which are near cones that are one way of saying this. Let's say I will define these things in a moment. Near cones that are Cohen-Macaulay, which is a homological property, but we'll see in a little bit. But in actually it's more general result. And what I will talk today is about that we extended Russell's result from we extended Russell's result in the sense that now we showed it for not only for EKR but for we proved a strict EKR in this setting of near cones that are Cohen-Macaulay or more general, and this class of complexes actually sequentially Cohen-Macaulay, but this class of complexes contains the chordal graphs with isolated vertices and contains a lot of the previous results about disjoint union of graphs. So that's why this class of complexes is important. Let's see. So concretely, what did we show?
So originally, is there a particular motivation for considering disjoint union of graphs?
Yeah. A motive for disjoint union of graphs. That's a good question. Yeah, I'm not. Yeah, I don't.
It's just like a join when you look at the simplicial complex, right?
Yeah, it's a general.
And so if the conjecture is true for a bunch of simplicial complexes, is it true for the join?
It's true for. It's true for. That's it. Yeah. Yeah. I don't know. Yeah. I just need one slightly technical definition, but I will try to have them motivated. So there is a notion that in topology that a simplicial complex looks like a sphere in a sense, which is a simplicial complex case. Cohen-Macaulay, if for every phase the homology of the link of K vanishes. Just bear with me for a second. For every dimension lower than this. So if you don't know what Cohen-Macaulay is, you can just think of the independence complex of a chordal graph, and this all holds for that. There is a parameter that we look at, which is the depth of a simplicial complex. One way of characterizing it is the maximum integer d, such that this homology I mean everything is over a field for every phase in K I less d. Yeah. Now I can state our result, which is if we have a simplicial complex K, depth of K minus 1, K less d over 2, then strictly less than plus strict K EKR. So instead of looking at the minimum facet cardinality with depth and shifted with respect to a vertex A, shift with respect to a vertex A, meaning that if you do a combinatorial shifting on this simplicial complex, sending any vertex to some vertex A, the apex, the simplicial complex will not change. So you can, to visualize this, you can think of the independence complex of a chordal graph with an isolated vertex. Yeah. And similarly to the Hilton-Milner theorem, I'm about to delete, but we have also a result in a similar fashion. That if one adds enough isolated vertices, we ask that K is shifted with respect to K plus 1 vertices, meaning that we can shift anything to any of these vertices, but between them we need to respect this order. If we are in this setting and we have F pairwise-intersecting family of faces of size K, such that intersection of them is empty, then its size is at most to be at most the faces of size K that contain V1 and intersects V2 up to Vk plus 1 plus 1, where this 1 comes from this one. So the maximal family is given by everything that contains V1 and intersect this plus this K set, like similar as in the setting of the Hilton-Milner theorem. Why depth instead of minimal facet size? At least for this theorem, Peter Borg provides a construction where the maximal family that is non-trivial, meaning that it's not a star, the maximal family that is not a star is not obtained by a Hilton-Milner family. And the example is quite simple, but so for example, one can take the simplicial complex with 4 elements here, 6 elements here. So this is 2 simplices that share 4 vertices, and you can consider pairwise intersecting family of faces of size 5, and the maximal the maximal Hilton-Milner type family will be when you take somebody from here. This is your x, and the guy disjoint from x will be some b, and it must have 3 vertices inside and 2 vertices in one of these guys, but there is a better family, which is consider everything that has 1 intersects the other 3 guys, and 2 guys from here, and these 3 guys. So one has to do the computation, but Borg showed in 2013 that at least for the Hilton-Milner type result, minimal facet size is not the correct parameter. So that's one of the motivation to look for another parameter. Why we look for depth is because it works with our techniques. So, and what do I mean by our techniques? Is that what we do in these 2 theorems is that we reduce like the main idea is that we reduce the problem from a simplicial complex, from an arbitrary simplicial complex to a shifted one. And you need to be careful doing this because like you cannot just apply combinatorial shifting because you might break the minimal facet cardinality property. So you might end up with a shifted complex, but you might not have the minimal facet size being the same. And so what we do is we apply another shifting operator called algebraic shifting. This was introduced by Kalai, and he has a survey. It was introduced before 2002, but that's where a lot of the properties we use are stated. That will denote shift x of k, and basically this operator reduces everything. It produces a shifted complex if from any simplicial complex. But the hard part of working with this is that predicting the output is difficult. Usually, combinatorial shifting is an iterative procedure. This works in one step. So actually predicting what is the output for certain families is an important question. In this, for the proof, we are not as ambitious to predict how this simplicial complex will look like, but some of the properties we can say how they will behave. Like some of the things this operator preserves is that it preserves the pairwise intersecting property. So if you start with something pairwise intersecting, you will end up with something pairwise intersecting. It produces something, a family that is shifted. It preserves inclusion, and the most important one, but important one for us, is that if you started with something with a simplicial complex that has the k minus 1, then the shifted complex will have the same depth, but moreover, its minimal facet size will be d, and this is one of the main reasons we are using depth and using this operator, because it gives us a simplicial complex with the same depth. And so so I said we don't know how to predict the output. So how do we use it? Well, what we do is we will modify our pairwise intersecting family in order that it has something we call a simplex boundary. So it will have all the case sets for some k+1 set. And this is, in a sense, this witnesses that F is has empty intersection, but also is a witness for homology. And because this operator preserves Betty numbers, one can conclude that the shifted family will also have this simplex boundary. So using this last property, what we do is that if we started with something that is has empty intersection with this witness, we can ensure that after shifting it with this algebraic shifting, it will also be non-trivial, and then we can apply the results then we can apply the results for shifted complexes, since we know that the theorem does hold for shifted complex. So there is a small detail in what I'm saying, is that okay, what happens if we can't ensure that if we can't ensure this, or how do we ensure it, right? And so to do it, now I'll just sketch proof. So the idea is that since we know that the simplicial complex has this apex vertex, which if you shift to it, the complex doesn't change, what we will do is we will try to shift all the vertices to the apex vertex while we don't break, while this results in a non-trivial simplicial complex, while we don't break this property of being if the thing goes through, meaning that we end up with something that is non-trivial, then there exists some f without the apex, but since it is shifted with respect to the apex, all the subsets will be in the family, and then we apply the shifting argument to reduce it to a shifted complex. The problematic part is that if this becomes trivial at some step, and if it becomes trivial at some step, we go one step before, so we have a non-trivial family, and what has to happen is that every member of F has A or V or let me call it W or both. So it became trivial and the intersection of this is non-empty, so there is some element in the intersection, so I go one step before, and in the previous step everything must have A, W or both, because if it doesn't have any of this, it's not affected by the shift. So there will be something, the intersection would be empty. And moreover, if the apex is not in an element, then well, we know that W must be there, but F minus W union A is not in the family. Because if this guy was in the family, then the combinatorial shifting wouldn't affect F, and it would be a witness for that the intersection is empty. And having this last part, what we can do is we can define an injection from the family to the k-1 faces of the link of the apex, which does what one would expect. If you have A, remove it. If you don't have A, that means that you have W, and you remove W. And so now, because of this last part, this map is injective, and the proof reduces to showing that it's not surjective. And to do so, we can build two Sperner families and apply the classical result on bounding the size of two Sperner families to show that we have somebody here that is not in the image. Let's say which are the Sperner families. So basically, we can consider we take some element in the family that doesn't contain A, and so W is there, and we define, and we take a facet that contains this C0, but also A. We can always do this because the Simplicial complex is shifted with respect to A. So if I have a facet that doesn't contain A, I can exchange a vertex different from C0 with A. And then I can take the following two Sperner families. One is maximal sets in intersection T. And the other one is P of C. A is not in C. And this is in F. B in C. So basically, this is the union of these two families. When I look at the k-1 sets, is the image of phi in this link, and they are cross-intersecting because the B and C are pairwise intersecting, and since A is not in C and W is not in B, they intersect in something that is different from B and C. So all they live in T minus W, and they will intersect in the facet T minus W. So we can bound the size of their sum cross intersecting, which is T minus 2, T minus 1, plus 1, and because T is at least D, which is strictly greater than 2k, this is strictly less than T minus 2, k minus 1, which is all the k minus 1 sets in T minus AW. So there is somebody that we do not attach with phi. I have 5 minutes? Yeah. What do I want to say? Yeah, like we can see that they are indeed non-empty. Since if you have somebody that doesn't have the W, it must intersect the C0, and it must do so in somebody different from W and A, so it will intersect inside the T. So that shows that this set is not empty. and this one is non-empty because phi of C0 is there. Yeah? So they are non-empty, cross-intersecting, and we can apply the cross-intersecting theorem by Hinton and Milner to upper bound it. So in a summary, to prove the theorem, we used combinatorial shifting to split into two cases. One case was handled using this other operator called algebraic shifting, and it's a short analysis, but kind of algebraic shifting does all the work for us, and the fact that we know the result for shifted complexes, and if in the harder case, we just argue by reducing the problem to a facet. And we argue combinatorially using the cross-intersecting theorem inside this facet to guarantee there's somebody in this facet that we do not attain. That's all. Yeah.
Any questions?
You mentioned that this question has something to do with homology.
Yes.
Does it have anything to do with cohomology?
With cohomology.
Yes.
Thank you. So in this case, you can we only care about actually the Betty numbers. So in this case, the dimension of the homology is our field. So it's the same. I could have said cohomology, but yeah.
Another question. The cohomology property and the depth for the simplex is the same for the stack random ring associated.
Yeah, there is a plus minus 1 there going on, but up to plus minus 1, yes.
If I remember correctly, you mentioned that in your main theorem, the conditions are kind of generalization of the chordal graph was isolated vertex case.
Yeah.
Then is there some interesting family that covered by your theorem?
Oh yeah, sure. There is a generalization of. Okay, there are several generalizations of chordal graphs, but one of them is that you allow. So for chordal graphs, the only induced cycles are of length 3. But now if you allow induced cycles of length 5 as well, so these are the only induced cycles that you have, this still holds. Another thing you can do.
So what's the independence complexes going forward?
It's sequentially it's vertex decomposable. It might not be pure.
Okay.
And so this is one family. The other family is, so the advantage of working with depth is that, one advantage is that you can take disjoint unions and you don't care which graphs are in the disjoint union. So the previous results were for disjoint union of certain graphs, but if you take the disjoint union of D graphs, like a graph with D connected components, it will have depth at least D minus 1. So that's one of the strengths of working with depth.
Is there relationship with depth of simplicial complex and other parameters? So since I see the definition of depth first time.
Yeah.
One thing I checked was if simplicial complex is a triangulation of d-dimensional manifold, then depth looks like same with the D.
Yeah.
And is there any relation with the Rayleigh number or those kind of any other stuff?
Probably through Alexander duality. Yeah, because Alexander duality gives you relationship with Cohen-Macaulay and Dilleray. So yeah, that's my intuition. Through Alexander duality, you might have a relationship.
Is there, I have a question. So is there some corollary of this theorem in such a way, like some theorem, some analog of Erdős-Ko-Rado, where you see the only proof is this and that some problem sets.
So at least for me, I think the selling point would be the chordal graph, the chordal graph with an isolated vertex. That was not known.
Chordal graph, independent sets.
Independent set of chordal graph. Yeah. The fact that this has the strict EA. This was not known. I guess this is the most appealing because the chordal graphs are more studied.
Any other questions? So if not, let's end the